Up till now, the information given about the triangle has led us to find a single triangle. Sometimes when we use the law of sines, the given information results in no triangle whatsoever or multiple triangles. Let's go through a couple examples to see how this works out. We're given that the length of side A is 3, the length of side B is 2, and the measure of angle A is 50 degrees. We can use the law of sines to try and find the measure of the angle B, because the sine of the measure of angle A, 50 degrees, over the length of side A, 3, is going to equal the sine of the measure of angle B over the length of side B. So I get that the sine of B is 2 times the sine of 50 degrees divided by 3, so the sine of B is about 0.510696. Now what we can do is find the measure of angle B by taking the inverse sine of both sides. So the measure of angle B is the inverse sine of 0.510696, and I get that B is approximately 30.7 degrees. Now, had this computation given me a quantity that was less than -1 or greater than +1, I would have no sign that gives me that result, because the range of the sine function is all real numbers between -1 and 1. As it stands right now, we believe that the measure of angle B is 30.7 degrees. The question we have to ask ourselves is, may there be an obtuse angle that would also give us a triangle with these dimensions? First off, we can tell right away that that won't be the case, but we'll work through it anyhow. We can tell it won't be the case because the measure of angle A is 50 degrees and the length of side A is 3, which is bigger than the 2. So I can't have an angle B that's going to have a measure of the angle bigger than 50 degrees because the length of side A is bigger than the length of side B. But the process would go like this. I try and find an obtuse angle B2 by taking 180 degrees minus the 30.7 degrees. And I would get 149.3 degrees. Now I know for sure that this can't be the case because 149.3 degrees plus 50 degrees is 199.3 degrees, which is bigger than 180 degrees, which is the measure of the sum of the interior angles of a triangle. So I have angle B is 30.7 degrees. I know the length A, the length B, and angle A. I can find angle C by taking 180 degrees minus 30.7 degrees minus 50 degrees, and I get that the measure of angle C is about 99.3 degrees. Now I can use the law of sines and say that the sine of 99.3 degrees divided by the length C equals the sine of 50 degrees over the length of side A, 3. If I solve this, I get that C is approximately 3.86 units. So now the longest side is opposite the largest angle, and the shortest side is opposite the smallest angle, so I should feel reasonable that my answer is correct. Now let's try another one. In this next problem, we're given that B equals 4, C equals 6, and the measure of angle B is 20 degrees. Since we're given the angle B and the side opposite, and we're given side C, we're first going to try and find the angle C. So we have the sine of the angle C over 6 equals the sine of the angle B over 4. This gives me that the sine of the angle C is going to equal 6 times the sine of 20 degrees over 4. If I take the inverse sine of both sides, I'm ultimately going to end up with that C is about 30.9 degrees. Now the question is, could there be a second triangle that exists? See, notice how B is 20 degrees and the side opposite B is 4. This angle of 30.9 degrees is bigger than 20 degrees and C is bigger than 4. So it's possible that I'm going to have a second triangle. I'll call the first angle C, C1. The second angle C would then be 180 degrees minus the measure of angle C1. So 180 degrees minus 30.9 degrees is going to give me 149.1 degrees. 149.1 degrees plus 20 degrees is 169.1 degrees. So I have not gone over the 180 degree mark. Therefore, I'm going to have two triangles. So I separate these guys out. Now, the measure of angle A1 is going to be 180 degrees minus 20 degrees minus 30.9 degrees, or A1 is going to have a measure of 129.1 degrees. To find the length of side A1, I take the sine of 129.1 degrees divided by A1 equals the sine of 20 degrees over 4. If I solve this for A1, I get that A1 is about 9.08 units. Over here, I would have that the angle A2 is 180 degrees minus 20 degrees minus 149.1 degrees, or that A2 is 10.9 degrees. Then, to find the length A2, I take the sine of 10.9 degrees divided by A2 equals the sine of 20 degrees over 4. Solve this for A2, I get that A2 is about 2.21 units. So there are the results of the two triangles.